I'm really excited to give this talk for three reasons. First of all, out of gratitude. You know, we have a great group, a great astronomy group here, particularly extragalactic people, and to have so many colleagues among the faculty, the postdocs, and the graduate students, and to get to have daily conversations about this stuff. It's really more than a pleasure, it's a real privilege. Okay, number two, this may be the only talk in my career that combines a question, some reasonable hypotheses, a test of those hypotheses, and the result. And this is how science is supposed to work, but for me it doesn't work that way that often. So, and the other reason is that if I'd given this talk, say, a month ago, I would have said that the result was very different. I would have said, well, we're saying something nuanced by combining observations of, this is a quasar spectrum down here, which has got this big empty space in the middle, and the galaxy data that we're collecting that look like these. We're saying something sort of subtle about the end of reionization, but I don't think that's true today. I think we're confronting a very fundamental question about how well we understand the early universe, and I hope to convey that to you during the talk. Okay, so first of all, to acknowledge the team. Elisa Bora has been an outstanding postdoc, and I will mention but not go through her work in great detail because you should hear Elisa do it. She's done some fantastic work. And Craig and Holly, Craig Douglas and Holly Christensen are also adding to this in fundamental ways. So I'm grateful to them. Here's what we'll do. I want to give you just a brief overview of the intergalactic medium, which we call the IGM, and then talk about what we know about reionization, which, as I'll describe, is this transition in the early universe where we go from a predominantly neutral universe to one that is ionized, the way it is today. And then I'll describe some of our team's efforts to combine observations of high-redshift quasars and galaxies in the same place at the same time, and what that's telling us about the evolution of the early universe. Okay, so to get on with it. So the first thing to say about the intergalactic medium is there is a lot of it. That is where most of the stuff in the universe is. Most of the matter in the universe is not in galaxies. It's out in between galaxies in deep space. And depending on the epoch you're talking about, this could be 90% or more. And that's dark matter and the baryons as well. And there are a couple of reasons why I like studying the IGM. Number one is quite intimately connected to cosmology in the sense that, you know, if you know the basic cosmological parameters of your universe, you can run a computer simulation and predict what the large-scale structure of the universe should look like. So in a way, I would say maybe after the CMB, what we know about the IGM is our most direct connection to the basic cosmology of our universe. At the same time, however, there's an intimate connection to galaxies, because not only do galaxies form out of the densest regions in the IGM, but the radiation and the chemically enriched gas and the energy that comes out of galaxies transforms the gas in deep space in a fundamental and, importantly, measurable way. And so, depending on what you want to do, you can use the IGM either to do cosmology or to do galaxy formation, but you sort of have to understand what both are doing at the same time. So the questions that my group answers are sort of two. What are the characteristics of the gas in deep space? That is, how do we characterize the intergalactic medium? And then, what do those characteristics tell us about cosmology and galaxy formation? So those are the big picture questions. Now, for a long time, our standard tool to study the IGM, because it does not emit much light of its own, are quasar absorption lines. So quasars, for Fred and Gabby's purposes, are fantastically interesting objects involving, you know, the extremes of physics, right? Fred is nodding enthusiastically. For me, they're just flashlights, more or less. They're quite bright and therefore useful. And the light from these things travels through the gas in deep space, and we pick it up with Keck. So this is the spectrum of one of those objects. This is at a redshift of 3.6 or so. This is the strong hydrogen Lyman alpha emission line here. And there are sort of two sides to the spectrum. Now, on the left, on the blue side, you're seeing lots and lots of absorption from hydrogen in deep space. This is the hydrogen Lyman alpha transition. It's tracing the neutral atoms that are out there, the neutral hydrogen atoms. And a remarkable fact about even an individual quasar spectrum is that it probes a huge range of scales. So one spectrum, one line of sight, stretches 600 million. I just came from class, so I'm down a brain cell or two, but 600 million parsecs. But at the same time, it's tracing gas on the scale of individual filaments in the IGM. So the dynamic range spatially is huge. On the other side of the spectrum, and we won't talk about these much today, but it's sort of the other half of what my group does, are the lines from metals. Elements heavier than hydrogen and helium. So we're after things like carbon and oxygen. That's tracing what's happening right in and around galaxies. And there's a lot to say about that, but we won't go into it today. Today we'll stick mainly with the Lyman alpha forest, the absorption due to the hydrogen in deep space. This is an animation of what happens and how we get the information from the IGM. This is a quasar spectrum as it's just been emitted. This is in the rest frame ultraviolet. And to throw up an energy level diagram of hydrogen here, there are a couple of transitions that we can be aware of. So the first is the n equals 1 to 2, that's Lyman alpha. There's Lyman beta, 1 to 3, so on and so forth. Those match up right there and there in the spectrum. And if we run the movie forward here, what will happen is that light travels through deep space, and when it encounters a cloud of gas, whatever part of the spectrum is right there at that special Lyman alpha wavelength can be absorbed. And so we see a series of Lyman alpha absorption lines along with Lyman beta and higher order Lyman series because of the cosmological redshifting of the quasar spectrum. And that means by the time it gets to us, it's got a sort of fingerprint or a barcode telling us where that light has been, and something about the characteristics of the gas, like the density and the temperature and the chemical mix of elements in there. Now, increasingly, what we do is a combination of observations, and it's certainly nice to have access to Keck here, and very good modeling. So this is done largely on big computers. So Anson, Simeon, Laura, they're the experts on that side of things. The trick is to sort of predict what these quasar spectra should look like to the degree that they resemble the observations very well. This field benefits from the fact that you can model this absorption quite well, because again, it's intimately tied to cosmology, and the sort of astrophysics that's on top is normally a bit of a perturbation, you might say. Okay, so now for those of you outside the field, you just have to eyeball it and tell me which one is real. Right? So one of these is real, and the other one is a fake that comes from, okay, it's a simulation. Maybe fake is too strong of a word. It's not that one. So one's data, one is observed data, and one is simulated data. Which is which? Which one is made by a computer? And you know, it doesn't. I know you don't look at these data sets, but you just know, right? Like there's the noise characteristics aren't right, or there's something too perfect about the simulated one.
Is the top one the fake one?
When theorists do this, the joke is that both of them are simulated. The joke here is I forget. I think that's true. Okay, let me tell you a little bit about how we use these data. So the idea is we make observations, then we run simulations, and we adjust the parameters in the simulations until they look exactly like the observations. That's the name of the game. So one thing we can do is we can take, so this is a little bit of simulated Lyman alpha forest. You know that because it's got no noise. And that's what it sort of looks like in one universe. If we do something like just decrease the amount of neutral hydrogen in deep space, then that means there'll be less absorption. And this is a pretty straightforward thing to measure. So the blue line here just means less neutral hydrogen in deep space. Now, we know cosmologically how many hydrogen atoms are out there. So if you can measure the fraction of those atoms that are neutral, then you know something about the ionization state of the gas. And that means that you know something about the radiation field, because this gas is photoionized. Now, we've done this, and this gamma here, this is a photoionization rate as a function of redshift. So this is sort of traversing the epoch of peak star formation almost back to the epoch of reionization. And what's interesting is that this photoionization rate stays pretty flat until you get close to redshift 6, where it takes a dive. And we'll see how that might be significant. So that's if you're a neutral hydrogen atom sitting out in deep space, this tells you how rapidly you get ionized. That's one thing we can measure. You can also turn that into a measure of how rapidly all sources of ionizing photons are producing ionizing photons and getting them into the IGM. There is a huge industry in scrutinizing galaxies directly and quasars directly to measure how many ionizing photons are escaping from those sources. We can do the same measurement, but from the point of view of the IGM. That is, we can look at the conditions of the IGM and tell how many ionizing photons are getting out. Now, the units here, they don't necessarily make much sense. Directly, but it's energy per unit time, per unit volume, per unit frequency is a function of redshift. What's significant here is that these are the measurements here, the sort of blue shaded region, again, stays sort of flat. But that's significant because galaxies don't do that. That if you go up in redshift, if you go back in time, there are fewer galaxies. There are also fewer quasars. That means fewer things that should be producing all those ionizing photons, and yet the number that they emit into the IGM is relatively flat. That tells you something is changing about the galaxies, and that will become important as well. Okay, another way, which is relevant to other people here, that we sort of poke and prod the IGM is to try and use it to constrain the nature of dark matter. So here I'm showing two simulated universes. One uses cold dark matter, and you see lots of fine detail. And the other uses warm dark matter, where a lot of that detail is washed out. And the motivation here is to do something to solve the fact that the problem that we have perhaps too few small galaxies, too few small satellite galaxies. If you adjust dark matter a little bit, maybe you could do that. You cannot do this without a penalty, however, because you can examine this choice by looking at quasar spectra. And here again is a simulation of the Lyman alpha forest. The green here comes from a cold dark matter universe with lots of bumps and wiggles, lots of structure, and the black from a warm dark matter universe where some of that structure has been smoothed out. The differences that we're going after are not quite that extreme, but our constraint at the moment from the data that we've looked at is that the mass of a warm dark matter particle has to be greater than about 5 keV. And that number is significant because it sort of rules out the most basic warm dark matter models that have been invoked to explain issues of galaxy formation. It is not the kind of dark matter model that people like High-Bow are working on. That gets around this problem to some degree. But anyway, we can use the IGM to study dark matter. And it's, again, because it's a sort of simple system where we understand the physics. But that's not what we're going to talk about today. We're going to talk about a point in cosmic history where the intergalactic medium is not simple at all. This is reionization. And reionization is the name given to the period of time in between when the universe was neutral, some time after the hot Big Bang, and when it was ionized. So we know it was neutral because the universe had long enough to expand and cool, and the atoms recombine, and it was neutral. And it would have stayed that way, except for the appearance of the first luminous sources, the first galaxies, the first supermassive black holes that pump ultraviolet photons into deep space and ionize it again. And these are light cones here, so these are relatively large-scale simulations. These are in megaparsecs, whereas the distance from here to Andromeda is about 1 megaparsec. So this is a relatively big piece of the universe, although not huge, as a function of redshift. So you're just sort of seeing how this transition goes from a neutral universe in orange to an ionized universe in blue. And there are three cases here. One where it's driven by rare sources like supermassive black holes, AGN. Another two where it's dominated by smaller star-forming galaxies, but one where it happens very, very late, and one a little bit earlier. And we're trying to figure out sort of which of these models is closest to reality. So studying reionization is significant, I think, for three reasons. In other words, we want to answer the question, why do we care? So number one, it's a major phase of cosmic history. I think we'd be a little dishonest if we said we understood how galaxies emerged and structure took shape without understanding this major phase transition in the universe. So that's one goal. Number two, there's a lot of galaxy and IGM astrophysics that goes into making this picture. There's a lot we don't understand, and I'll be explicit about that shortly. But it relates to both how galaxies work and how the IGM works. We want to know that. And finally, it has implications for cosmology, because reionization has an impact on other probes of cosmology that we depend on. For example, it affects the observations of the cosmic microwave background. It also affects the way we use the Lyman alpha force, the IGM, to constrain dark matter. So if we don't understand reionization at a detailed level, we will always be limited in how well we can study cosmology. So that's the motivation. All right, let me tell you a little bit about what we do know. Okay, this is what we do know about reionization. There's sort of three parts. Number one, by looking at these quasar spectra, now these are among the first quasars that were discovered above redshift 6. And redshift 6 corresponds to about 1 billion years after the Big Bang, and that's a sweet spot for when we think reionization occurred. We believe, oh, here you go. If you squint and look very carefully, this is the Lyman alpha absorption, what's left after Lyman alpha absorption in the IGM. There's a little bit getting through. But the IGM is incredibly good at absorbing Lyman alpha photons. If the IGM were neutral, the optical depth would be 100,000. It would be totally black. Nothing would get through. In order for Lyman alpha to be transmitted, the universe has to be very highly ionized. So the fact that you see even a little bit of transmission means that the IGM is ionized, and that means reionization is done. So these quasar spectra tell us that reionization is over by about a redshift of 6. And again, that's about 1 billion years after the Big Bang. That is not me. This is Bob Becker up in Davis, who just retired, I think. And sometimes I think that I may have gotten my start in the field out of confusion. But if you didn't check, that's on you, not on me. All right. Next thing we sort of really know about reionization is its impact on the cosmic microwave background, of which we have exquisite observations now. And what reionization does is it leaves behind free electrons, and those free electrons scatter CMB photons. The earlier reionization happens, the more scattering occurs. This is quantified by an electron optical depth. It's got a number there, 0.05. This is the latest and greatest measurement by Planck. And that gives us a sense of sort of when, in rough terms, reionization occurred. And finally, I think, no, I'm quite confident, this is the next best measured thing is the thermal history of the intergalactic medium. And this was done by Elisa Borra, who is here. Now, what Elisa's done is to not measure directly the ionization of the gas, but the heating of the gas. Because when you ionize a parcel of gas in deep space, you also heat it because the photons have extra energy, and that energy gets carried away by the free electrons. So, and they get thermalized, and that heats up the gas quite significantly by tens of thousands of Kelvin. After that, the universe expands and it cools down. Now, what she's done is to take advantage of the fact that you can tell the temperature of the gas by this sort of smoothness of the Lyman alpha forest. If you heat the gas, you get more random motions, more thermal broadening, and those absorption profiles smooth out. That's the way you use it as a thermometer. But in addition to that, if you heat the gas, it also expands, right? And it expands in such a way that is measurable, and there's more bulk motion because the universe is expanding. So if you make something bigger, then end to end, there's a larger expansion velocity gradient. And that is also measurable. And Elisa has determined how to separate those two so that she can say both what is the temperature of the gas and how much heat has it received over all of cosmic history up to that point. And the insight that we could measure this heating parameters, this sort of energy per baryon, was given to us by Fahad Nasir, who is here as a postdoc as well. This is what it looks like. So this is temperature. This is total heating, energy per baryon. And these are several different reionization scenarios showing you the thermal history. And these quantities can change based on if reionization happened at a given redshift. that obviously depends on the temperature boost that you get right when reionization happens. There's the boost, and then here's the cooling due largely to adiabatic cooling. It depends on when reionization occurred. Earlier reionization means more heating by the time we make these measurements, and it depends also to some degree on the spectrum of the sources that are doing the ionization. If you put all that together, you can put quite good constraints on when reionization occurred. Now here are two constraints. This is a likelihood function of redshift, the sort of midpoint of reionization, let's say. Now, the red line is for Planck. That's from the CMB measurement. The green line is from Elise's work. And you see they nicely overlap. And what it's pointing to is a sort of midpoint reionization of around 7 or 8. Now, there is a very significant difference between these two, apart from the methodology. This red line is a 700 million euro satellite. The green line is about 8 keknites, plus 1 Elise, of course. They give comparable results. All right, so that's what it's pointing. It's pointing to a sort of redshift about 7 or 8. There are other indications of things happening. This is one of them that I'll just mention briefly. Here's a spectrum of a galaxy. This is intensity as a function of frequency. It's an average galaxy spectrum, and it's got this Lyman alpha emission line. Galaxies don't all have them, but on average, you see something. If you look at the fraction of galaxies that have this Lyman alpha in emission as a function of redshift, something very peculiar has been observed, which is that that fraction increases as you go from redshift 4 to 6, roughly, or maybe not so strong, but anyway, it tanks as you go above redshift 6. As you go into the reionization epoch, what we think is the reionization epoch, suddenly galaxies don't show Lyman alpha in emission anymore. And that's hard to understand because there's no reason physically that they should stop producing these Lyman alpha photons. Something is just getting in the way of us seeing them. And that is believed to be neutral gas in deep space, scattering by the intergalactic medium. And now there's a debate as to whether that requires big patches of neutral gas or whether there's neutral gas in and around these galaxies. But that's the observation, that something quite significant is happening over this redshift 6 to 8 interval. And again, it's pointing to a significant amount of reionization not yet completed by these redshifts. So to a broad degree, there's an amount of consensus, right? The consensus statement, the sort of, the going model is that reionization has its midpoint around redshift 7 or 8, which is several hundred million years after the Big Bang, less than 1 billion years after the Big Bang. And according to those quasars, it ends by redshift of 6. So this gives us something to work with, and it also presents a rather serious problem. So the problem is that there is not very much time between redshift 7 or 8 and 6. It's about 300 million years between redshift 8 and redshift 6. And if you want to reionize half of the universe, you've got to pump a huge number of ionizing photons into the IGM. And that puts certain requirements on the galaxies and the quasars to do that. Here's one way of looking at that problem. If you take all of the galaxies and all of the quasars from the absolute peak of star formation and quasar activity, which is around redshift 2 or 3, and you put them all there at the beginning of time, they will not complete reionization by redshift 6. So that means that the far fewer galaxies that actually are there have to work very hard. That is, there has to be something significantly different about those high redshift galaxies that lets them do the job that galaxies later on we know would struggle with. And there are people here, Brian, others, are working to figure out what is it about those galaxies that makes them so much more effective at ionizing the universe. And the question of what the sources actually are has been an important one. And you've got sort of two choices. They could be supermassive black holes driving active galactic nuclei, quasars. And, well, there's sort of two things you need. You need there to be enough of a certain class of objects, and you need those objects to be producing ionizing photons. And for quasars, we definitely know they produce ionizing photons, and they emit them, right? We see them getting out. The question is, are there enough of them? This is a luminosity function, so number versus luminosity here, brighter objects on the right. And you can use a luminosity function like this to ask that question, are there enough? And the answer is basically no. There are still some holdouts who disagree, but the smart money is that quasars can't do better than about 10% of the ionizing photon budget. So we're down to a Sherlock Holmes moment because, I'll say why in a minute, star-forming galaxies are the other option. And there we know that there are lots of galaxies. The question is, do they emit ionizing photons? There's no question that stars make ionizing photons. It's just the question of whether those photons get out. Here is a stack of lots of star-forming galaxies in their non-ionizing part of their UV spectra. And there is the stack of the ionizing photons getting out from the same galaxies. And you see what I see. There just isn't much, right? This is quantified as an escape fraction. So basically, I think the state of the field is that on average, galaxies don't really emit as many ionizing photons. And the question now is, which galaxies do more than their fair share? Is it low mass galaxies? Is it galaxies in a certain phase of their star formation? And again, we have groups that are working on that question. So that's one of the really interesting astrophysical questions. I said it's sort of a Sherlock Holmes moment because this is the impossible, right? I think. Unless something really surprising happens, we know that there just aren't enough black holes. This is really improbable. If you didn't know anything about when reionization occurred, you only knew something about the sources, you'd say, well, there's no way that reionization would happen before. It would take a couple of billion years at least to reionize the universe, given what we know about galaxies. And yet we know that it happens much earlier. So once you've ruled out the impossible, whatever is left, however improbable, has to be the answer. Got there. Okay. So what we'd like to do is sort of confront this picture of reionization. And as you go up in redshift, it becomes observationally far more challenging, right? What this talk will address from here on out is what more can we learn from the IGM near the tail end? Whether we're just at the end of reionization or just a little bit beyond, that's the most observationally accessible, place to work. And that's where a lot of our group has done its work. And the question is, are there interesting things happening there? And the answer, of course, is going to be yes. So this is the starting point. It's looking at the opacity, just the raw opacity in the Lyman alpha forest, asking how many Lyman alpha photons actually get through. This is a high-redshift quasar spectrum. This is the Lyman alpha forest that we looked at earlier. And if there were no absorption, this continuum would just sort of keep going along near the top of this red box. And the fact that there isn't much left means that a lot of absorption has occurred. And you can look at many quasar spectra and quantify the amount of absorption. This is a measure of the opacity as a function of redshift. And the opacity here is just minus log of the flux. It's a pretty simple measurement. In fact, we take big sections of the Lyman alpha forest spectra and measure this opacity. You see two things. Number one, the opacity increases as you go up in redshift. That's not totally unexpected because the universe gets more dense. Number two, however, is that once you get up above redshift 5, there starts to be much more scatter. And all these different dots are different lines of sight, and clearly they start to look very different from one another in terms of their Lyman alpha opacity. So what was observed starting with the first observations of high-redshift quasars, so this is a paper by Xiaoyi Fan in 2006, is this increase in the scatter. But shortly after this paper came out, another one, this one by Adam Litz, pointed out the fact that there will naturally be more scatter as you go up in redshift, as you go to earlier times. The reason for that is that when you go to very high opacities, the only places that transmit anything at all are the rarest, least dense regions of the universe. And if something is rare, that means you might hit one along one line of sight, but not another. And there will naturally tend to be quite a bit of variation, therefore. So this model didn't require anything to do with reionization, even though the observations sort of invoked that picture of patchy reionization that we've seen in the simulations. And that's where the field more or less stood for several years. So we came back to this recently, basically because of a single object, and it's this one. This is a quasar at redshift 6, it's its spectrum. And it's significant for 2 reasons. Number one, it's got a great big hole in the middle of it. It's missing light in the Lyman alpha forest entirely. The other thing that makes it significant is it's quite a good spectrum. You know, it's high signal to noise. It's 10 hours on an 8-meter telescope, and we have high signal to noise, and that means that we can say with great confidence exactly how little light is getting through, how dark this patch is, or this giant trough is. It's big. It's 160 megaparsecs. I think it sounds better if you say it in mega years. It's light years. It's 500 million light years across. And as far as I know, it's the largest known thing, which depends on your definition of thing. But I don't know of it. Correct me if I'm wrong, but I don't know of anything that is sort of discrete and different from something else that exists at the same time in the universe that is bigger than that. You got to have a claim to fame, I suppose. But anyway, whoops. However, it's large, but what really makes it significant is that it exists at the same time in cosmic history as other regions of the universe which aren't nearly so dark. This is another redshift 6 quasar. This is its Lyman alpha force, and there's much more transmission here. This is sort of more what you'd expect, and this is just bizarre. And then the question is, well, is that significant? Do you get this just by random fluctuations in the density field, or is there something more going on here? All right, so the way to answer that question is to, number one, get more data. So this is, again, the measurement of Lyman alpha opacity in the IGM as a function of redshift. All the points in here are data. These upward pointing arrows are lower limits from that dark trough. And then you have to go to a simulation and ask, all else being equal, would you expect that much scatter? So all else being equal means sort of a boring IGM that has a uniform ionizing radiation background in it, where the temperature is sort of the same everywhere in the gas. The scatter that you'd expect is this orange band here, and clearly that's exceeded by the data. All right, and so this has been improved on since by my student Sarah Bozeman and another group. This is Anna Eiler's both recent papers, but clearly we're seeing that there's something else going on here. It can't just be density fluctuations because the scatter is too large. And it's too large by quite a factor. It turns out you need at least factors of several fluctuations in the fraction of hydrogen that is neutral on very large scales. That does not happen at lower redshifts. If you average the universe on large scales, the neutral fraction is basically the same everywhere. But here it varies by factors of several. So that's really different. Okay, so what's going on? Well, you got choices. We need variations in the fraction of hydrogen that is neutral, the neutral fraction here. Now that can be driven by density fluctuations, but we've already ruled that out. The other choices are you can have fluctuations in the ultraviolet ionizing background. That's represented here by this gamma, because this is photoionized gas. Or you can have fluctuations in the temperature of the gas. And the temperature comes in here because of the recombination rate. The recombination rate depends on temperature, so if the temperature fluctuates, the recombination rate will as well. So absent fluctuations in density, which we understand very well from cosmology, there must be fluctuations in ionizing radiation or temperature. And since those observations came out, there were a set of models that invoked these factors. And I'll just go through them briefly. So we'll start off with fluctuations in the ionizing UV background. Now in this model, the ionizing background comes from galaxies, and the key is that if you have a region with lots of galaxies in it, you'll have lots of ionizing photons. If you have a region with few galaxies in it, you'll have a much lower radiation field. Now that's fine so long as ionizing photons can't travel a long distance. Nowadays, and through most of the history of the universe, ionizing photons travel a long, long way, hundreds of megaparsecs. So it really doesn't matter whether you're next to an ionizing source or not. But if you constrict that range quite significantly, then regions with lots of galaxies in them, like a high density region like this one, will have a high UV background. A low density region like this one will have a very low UV background. And it would be the low density region where the hydrogen would be more neutral and we'd expect to find our long dark trough. Now, the difficulty is the need to constrict the flight of the UV photons. This is because this has been measured. This is the mean free path, the distance that ionizing photons travel on average as a function of redshift. And it's been measured fairly well from redshift 2 up to about a redshift of 5. I don't know, it looks like there's a relation. It looks like you could sort of extrapolate that out. We're working here close to redshift 6. This is where we'd expect the mean free path to be. That's where it needs to be, down here. And this is a log plot here, so that's a factor of many down from naive expectations. But maybe the universe works that way. A variant of that is to have rare sources providing the UV photons. And if you're close to a rare source, like a quasar, then you see plenty of ionizing photons. And if you're far away, you don't. And if those rare sources are sort of, well, they're rare. So it only matters whether you're close to one or not. And so our long dark trough could live in any region with a low UV background, provided you are sufficiently far away from a quasar. The difficulty there, again, is this question of whether there are enough quasars. And people like Anson have answered this in different ways. Number one, just counting up quasars, it doesn't look like it. And Anson's particular contribution has been that if there were enough, and quasars did reionize the IgM, provide all these ionizing photons, they would also have ionized the helium in deep space. We know that that happens significantly later. So quasars are sort of out, but I include this model anyway for completeness. All right, and the other one, and this is Anson again, is that there could be fluctuations in temperature. And again, that impacts the recombination rate. So in this case, it has to do with when reionization occurred. So at reionization, as I said, you get a big boost in temperature, and then you cool down. So a region that reionized early would have plenty of time to cool down and would be relatively cool by the time we observe it, by the time we're seeing this long trough. A region that reionized only shortly before would still be hot. And it would be the colder region where we'd see our long trough. And not only would it be colder, but a place that reionized early would be dense. It would have more galaxies. It would have more gas. It's got more gas there to do the absorption. So it would be natural to expect that, high density over here, high density where you have lots of gas that has had time to cool down would be the place where you find the long trough. So, which is it? Well, it turns out they all do a good job in reproducing the distribution of opacities that we observe. I showed you this plot of opacity versus redshift. There was this big scatter. This is putting that scatter in terms of an accumulative distribution. This is the distribution of opacities. These are our long troughs way out here. There are 3 different models in solid lines, the 2 UV background fluctuation models and the temperature model. You can make them all work in that sense. So how do you tell them apart? The trick is that they make very different predictions for where you should find that long dark trough. So if you're paying attention, the UV background fluctuation predicted that a long trough should be in a low density region with few galaxies and few ionizing photons. The temperature model predicted that it should be in a high density region with plenty of galaxies that reionized early and had time to cool down. They both can't be right. Well, actually, both effects should be in play at some level. And the question is really which one dominates. Okay, and that sets up a test. If we can figure out whether that long trough lives in a high density or in a low density region, then we'll sort of have our answer. We can't see the gas, but we can see the galaxies. And so what we would like to do is to use galaxies to trace the density field. This is the UV background model. The grayscale here is now the Lyman alpha opacity, so black is where we'd find our long trough. That would be in a low density region here in the UV background model, but it would be in a high density region in the fluctuating temperature model. And if we can just go out and count galaxies, then we might be able to figure that out. And of course, we can count galaxies. Now, it turns out nature has done us an enormous favor by giving us a very good tool to count galaxies just at the redshift that is at the center of this long trough. Here's the long trough again, so its intensity is a function of wavelength. This is a filter curve for a narrowband filter that has been used extensively to find a particular type of galaxy at a redshift of 5.7. It picks up Lyman alpha emission at redshift 5.7, and this has been widely used to do surveys for Lyman alpha emitting galaxies just at this redshift that's going to be helpful to us. So the thing that we need is to be able to, okay, we can find galaxies at that redshift. We also need to be able to go big, because this is sort of a large area question. And we need to be able to go deep. Deep because we're going to need lots of galaxies to sample the density field well enough. And large because this is, we're talking tens up to 100 megaparsecs, and that's a big field of view. It turns out the Subaru telescope is ideal for this. So we get Keck time directly, but we have an agreement with the Subaru telescope to trade nights. And we've taken advantage of this to do some observations with Subaru to test these models. This is how it works. If that galaxy is there, then its Lyman alpha emission will show up in that narrow band, and it will be absent normally in the other two bands. That's just how we find them. And this is a tried and true method. Barham has done tons of this. My group is coming to it for the first time. This is the field. We went out, we got the data. It took some time, but we did it. This is the field. It's a 1.5 degrees across. It's huge. It's one field with the Hyper Supreme Cam on Subaru. We got deep enough. There are plenty of galaxies here, and you can sort of begin to see structure in the distribution of those galaxies. And the quasar line of sight is right in the middle. And the question we were after is this a high density or a low density region? Now, given our recent exercise in democracy, I thought we could put this to a vote. For those of you who don't know the answer, I invite you to look in your heart of hearts and decide whether the most opaque region in the universe is high density or low density. Take a moment. All right, high density, which would mean lots of galaxies. And now low density, few galaxies. This, of course, is a sham election. We're not really counting votes. But it's low density. They're upset. We're actually doing a sort of recount. But anyway. All right, if I transform that into a density map, it looks a little clearer. So this is the quasar. The quasar line of sight goes right through the middle. Each of these little dots is a galaxy, and there just aren't many in the middle here. So dark means low density. It's low density quite clearly. If you measure it, this is the surface density in annular radii as a function of radius away from the middle here. It's low density in the middle, and then it recovers to the average density as you go further out. So there's a deficit of this particular type of galaxies, Lyman alpha emitting galaxies close to the line of sight. And to first order, that probably means it's a low density region. So the darkest place in the universe is a low density region at these redshifts. And we can go back and compare to the models that were put forward. So these are now the predictions for the surface density of the Lyman alpha emitting galaxies as a function of radius away from the center. And the spread in the models is shown by the colored band. So this is the fluctuating UV background, which required that it be low density. This is the fluctuating UV background from quasars, where that dark region could be essentially anywhere. And this is the temperature model that required it to be at a high density region. That one looks good. That one, meh. But we sort of rule that out on other grounds. Again, there are problems with having quasars do the job. And the temperature model is challenged by this particular observation. Now, don't worry, the temperature fluctuations are going to come back. Because as Anson has rightly pointed out, they have to be there at some level. And determining their role it turns out to be, I think, one of the more interesting sort of follow-ons to this problem. So at first glance, the results support a picture where those large opacity fluctuations are driven by UV background fluctuations, and the UV background comes from galaxies, probably not quasars. There is a significant caveat. You know, we were looking at a region of space where Lyman alpha photons were strongly absorbed. Why did we expect to see any Lyman alpha photons from galaxies? And it turns out it's because the Lyman alpha photons we normally see are the ones that are slightly redshifted when they are emitted so that they don't get absorbed. They're just redshifted enough that they're redward of the resonance frequency, and they sail through, at least some of them. That's what we expect, anyway, normally. However, there is a more fundamental question here, which is, have we considered all of the relevant models? One thing you could ask is, okay, well, there's no Lyman alpha in the quasars. You saw very few Lyman alpha emitting galaxies. Maybe they're just big patches of neutral gas along that line of sight, soaking up Lyman alpha photons. If there are, that would mean that we're not studying the effects of reionization. We're studying reionization. We're in it. That there are big patches of neutral gas still left at those redshifts. Now, up until recently, I would have said, no, and I have evidence for that. This is the Lyman alpha forest, but up here in blue, I've plotted the Lyman beta forest. And Lyman beta is, primarily only different because it's somewhat weaker in terms of its absorption versus Lyman alpha. And you see some transmission getting through, though it turns out to be very little. And I would have said, well, look, there's a little bit of transmission in Lyman beta, and that means that the gas has to be highly ionized. But it turns out it doesn't have to be highly ionized everywhere. So, as Fahad and Anson have recently pointed out to me, you can have a line of sight like this one in their simulations. So the red here is regions of the IGM, they're ionized. The black is still neutral. And in this simulation, there are big patches of neutral gas. This is sort of in the simulation. This is what the Lyman alpha forest would look like along that line of sight. And it looks just like our dark trough. And this is the Lyman beta forest, which I would have said needs to also be completely absorbed if you've got big lumps of neutral gas. But in the cracks between those neutral patches, Lyman beta does get through. So it turns out that we cannot rule out significant patches of neutral gas along this line of sight. We may indeed be looking at the very end of reionization and not just its after effects. So, and this is from another group making a similar point. This is, again, light cones. This is going up in redshift to the right and back in time. This is the neutral fraction. The red is neutral going to ionized blue over here. So this is the sort of reionization picture that we have in mind. This is the gas temperature. As the gas is reionizing and it's heated, and those temperature, the fact that we have different places reionized at different times means there will be large-scale temperature fluctuations. You can see them just after reionization has ended. So those temperature fluctuations are definitely there, or should be. And then this will be the UV radiation field. What we thought was that we were studying this part of the story, perhaps just after reionization had ended, and we were trying to sort of make a careful inference about whether there were fluctuations in the UV radiation field or in the temperature. But it might be that we're studying this part of reionization, where there are still big pockets of neutral gas. And if so, that's exciting, because again, lower redshift is more accessible observationally. We can bring more, observation resources to bear at redshift 6 than we could, or redshift 6 or down to 5, than we can to redshift 10. Even though we'll have the help of things like James Webb Space Telescope and big ground-based telescopes. So how do we test? How do we tell? So I think that's the immediate question now in front of us. These features that we're seeing in the intergalactic medium, are they there because reionization is over and done with, or are they there because reionization is still ongoing? If it's still ongoing, that actually solves a problem for us. Because remember, we made the argument that if reionization was sort of compressed in time, that required galaxies to sort of make heroic contributions of ionizing photons. But if it's a little bit longer, then they've got more time. And maybe the physics of what drives that in galaxy formations is a little bit easier to understand, more compatible with what we observe at lower redshift. One way I think we'll tell is by getting better and deeper data, of course. I think it's probably easier to create those very long troughs if you have large sections of neutral gas. And it turns out that the one I've been showing you is not the only one we know about. This is another one. This is the second one we know about. And this is being written up by Craig Douglas, a grad student working in our group. This trough, it's not as easy to see here because we haven't stretched it out. But it's there. It's over 80 megaparsecs long, nearly as long as the 110 megaparsec one we showed you earlier. And not only that, but this particular line of sight stays quite dark, although not completely black, down much, much longer. And it could be that lines of sight like this are so odd that they require them to be probing the actual reionization epoch. And that remains to be seen. We're trying now to figure out what tests can we do to tell the difference now between this fluctuating UV background model and the sort of in the thick of it reionization model. Right, that's it. So here's the rundown. We have multiple ways of probing the reionization epoch, and they're starting to converge on a picture where reionization ends relatively late, that is sort of around 1 billion years after the Big Bang. The exact timing remains uncertain. The particular sources remain uncertain. We think it's galaxies, but we don't know exactly which ones. And then there are ways that we've been using these extreme fluctuations in the opacity, the Lyman alpha opacity of the IGM to tell something about how reionization ends. The observation that we highlighted here was that the most opaque region in the universe around redshift 6 is also one of the least dense. And of course, now we're trying to figure out, well, is it really as low density as we think? What about other lines of sight? That's the direction we're moving. But at the moment, it seems to indicate that extreme UV background fluctuations are there, which would be perhaps a remnant of reionization, or perhaps reionization is not yet complete by the epoch that we're observing. So we'll do more. We should learn, I think, in the year or two ahead, which interpretation is more likely to be correct. And once we know that, we'll know better how to train our observations and our modeling efforts to studying this period of history that keeps some of us busy. So thank you very much. Question?
Thank you, George. Very nice talk. Question?
The last Quasar you showed for Craig's paper, what redshift was that at?
So this is another redshift 6 quasar. And the trough here is spanning basically the same range. And it turns out it's only significant if you see one of these dark troughs at a redshift where other lines of sight show transmission. We are starting to study higher redshift quasars, we're up to redshift 7.5 now. And they definitely show these long, dark stretches of Lyman alpha forest, but you would expect everything to be dark at those redshifts. So it's the fact that we're seeing them below redshift 6 that is so significant.
How would these results depend, George, on the filling factor? So you have sort of fragmented sort of neutron clouds with IGM. So how would that affect it?
He's asking, how does the result depend on the filling factor of the neutral gas? So I believe that's something that Anson and his team are sort of addressing, right? Does the universe have to be filled up with neutral gas, or is it a few sort of neutral islands that can do it? There have to be breaks. We know that because there are these windows where Lyman beta gets through. I'm not sure that we've explored enough parameter space to answer that question yet. Does anybody have a speculation?
Parameters is model dependent then? It depends what model you have for distribution.
I imagine that the observations will tell us something about the filling factor and distribution.
Yeah, so one difficulty is that the simulations of reionization don't do a very good job sort of predicting the tail end, because that tail end is dictated by sort of small scale clumps in the cosmic web that we have difficulty resolving in our simulations. So it's tricky, but we're working on improving the models.
So you mentioned that if we agree reionization ends at redshift 6, then quasars are up to 10% contribution to that reionization process. And that probably could not be only due to the galaxies. So we need more resources for reionization. So could you please tell me what are the possible scenarios for this? What could be possibly responsible for the reionization? Could be due to some sort of, could that indicate that galaxy formation happened earlier than what we think?
So you're saying that I sort of made the case that it couldn't be quasars and it couldn't be galaxies. I didn't mean to make the second point quite so strongly. The point was supposed to be that what we have observed of galaxies so far doesn't quite square up with them producing enough ionizing photons. So the question is, do galaxies evolve in some way, or are there more of a particular type of galaxy, say low mass galaxy at high redshift, that emit these ionizing photons more easily? I don't know, is that a fair characterization?
Yeah.
All right.
We don't know. Yeah, we don't know what's causing. We assume that there's more ionizing photons escaping from high redshift galaxies on average.
But do we have a plausible explanations from your
We have lots of plausible.
Yeah.
How many quasars do we have in that sweet spot, kind of around, a little less than redshift 6 that are helpful for these kind of states, like how many sight lengths?
Oh, it's a bunch now. I mean, she's asking how many quasars do we have at these redshifts that are useful, and I think the most recent tally, it's something like 150 above redshift 6. It could be more now. So we're getting to the point where we're getting into a target sort of rich, field. But then the question is, how many of those are interesting? How many are worth spending extra time on to observe? And one of the things that we're doing is to, go from the sort of preliminary data, selecting good objects to observe more deeply and going after those.
All right, last question.
So if it turns out that the troughs are kind of more dominated by later reionization, what do you think the revision of that redshift would be from 6 to, I guess what redshift do you think that would be kind of revised to? Or is it too early to make it?
Kind of asking me to spitball when do I think reionization ends if the late reionization model is correct. It could be, well, I don't have to guess. The models that have been put forward so far have suggested that it lasts all the way until 5.3. And that doesn't sound a lot different from 6, but it is. I mean, it's, what is that, 100 million years, a couple 100 million years? It sort of makes the time window when things can happen significantly longer.